Hello, good day. You're welcome to our physics class. In physics, we shall be looking at the topic machines. We'll aspects of the topic and then we'll go straight into solving questions. Now, machines are devices by which work can be done easily and more conveniently. So, in case you want to achieve a task and you would need so much of effort or energy to carry out this activity, then you could look for a device which could reduce the efforts which is being applied in order to carry out the work or the task. So when we are talking about machines now, you've noticed that we've talked about the fact that you apply efforts, and that effort will be needed to move perhaps a body through a distance, and then we talk about a load which is being moved through a distance as well. So what we are saying now is that when we are talking about machines, we can't forget the aspect of load and effort. This load needs to move a certain distance, which we could represent as y, and the effort is applied to move through a certain distance. We can represent that with x. This is distance moved by the load, and this is the distance across which the effort is applied. Alright, when we consider the ratio of our load to the effort, it gives us a new term which we call the mechanical advantage, which is the ratio of load to effort. Another name for mechanical advantage is also force ratio. Now, when we consider the ratio of distance across which the effort is applied, which is x, to the distance moved by the load, we would arrive at another term which is known as the velocity ratio. So the velocity ratio is the ratio of distance moved by effort over distance moved by load. From all this, we are always trying to have an advantage whenever we are using a machine, and that is the mechanical advantage. And we can determine if a machine is assisting us to easily carry out the task which we want to achieve in measuring its efficiency. And so we would say that the efficiency of a machine is equal to the mechanical advantage over the velocity ratio times 100%. Here we expect the mechanical advantage to be lesser than the velocity ratio. To measure our efficiency, we say mechanical advantage over velocity ratio times 100%. And most times the mechanical advantage is lesser than the velocity ratio. The mechanical advantage is equal to the velocity ratio. Now in this case, meaning that the efficiency of the machine is 100% and there are no friction, because it is the friction that mostly causes the mechanical advantage to be lesser than the velocity ratio. When we consider that we are carrying out a particular work, which is called the work output. The work output is a multiplication of the load that we are carrying multiplied by the distance moved by this load. That's how we derive our work output. So we said work output is load multiplied by the distance moved by load. Then the work input talks about the effort you are putting in across a particular distance. So the work input we said is the effort multiplied by the distance across which it is applied. We could also use this to derive the efficiency of the machine. So the efficiency of the machine will be the work that is being produced, that is the work output over the work input multiplied by 100. So we are saying that we can get the efficiency using this formula, or we could use mechanical advantage over the velocity ratio times 100 over 1. And what does this mean? If you have an efficiency that is lesser than 100, it means that the work output is lesser than the work input. Likewise, the mechanical advantage is lesser than the velocity ratio. And 100% efficiency means that friction has been eliminated and some other factors. But really, do we have any machine that is 100% efficient? Well, that's the question. Alright, so next, we look at the classes of machines. Machines are classified based on the kind of work that they help us achieve or carry out. We have the lever, we have the pulleys, inclined plane, the screw, the hydraulic press, the wheel and axle, gears, and so on. Now let's take note that there are some of these that are examples of another. For instance, the screw is seen as one of the modification of an inclined plane. The gear is also seen as one of the modification of the wheel and axle. So all these have their own modification. Now when we talk about lever, something about the lever is that it is represented sometimes with a bar, and it has a point of pivotal for the load and effort. So meaning that when a load is attached here, there may be an effort to balance it up. So if we have a load here, we have an effort to balance it up. And we have three orders of lever. We have the first order, we have the second order, and the third order. When we are talking about the order, we are talking about the arrangement of the efforts, this point of pivotal, which is also called the fulcrum, and also the load. I'm saying that there are several arrangements of these three. Now, in the first order, this is a diagram of such, where the fulcrum is at the middle, such that when a load is applied here, the body tends to move down, and this tends to move up. But if the load will be carried easily, the efforts could be applied to this side, and the efforts applied will help to lift the load up, and the fulcrum can be adjusted. So if the fulcrum is adjusted towards this side, we will find out that we would not need so much of effort to lift heavy load. So it is all about adjusting the fulcrum in order to achieve a mechanical advantage and a higher efficiency. Now, examples of first order lever, we have the crowbar, we have the claw hammer, we have the plier. So in this, we have the fulcrum at the center. Next is the second order. In the second order, it is arranged such as fulcrum, load, and effort. And in this case, we have the fulcrum at the edge, at any of the edges, and then we have the load and also the effort. This is the arrangement of second order lever. An example of the second order lever, we have the nutcracker, the wheelbarrow, and so on. And then the third order lever, we have the load, effort, and fulcrum. And in this place, the emphasis is on the effort being at the center. So in this case, we have a diagram as such. The emphasis is on the efforts being at the center. It may be acting upwards or maybe acting downwards, but the important thing is that it is at the center. And then we have our fulcrum over here. Alright, so in the first class order, we have the arrangement as load, fulcrum, effort, or it could be the other way around, as effort, fulcrum, load. The important thing is that the fulcrum is at the center, and the second order we have the load at the center, and in the third order we have the effort at the other. Example of third order lever include the forearm, your forearm such as this, the tongues, that is the sugar tongues, and so on. Now the pulley is a system of fixed or movable wheel with a rope that passes through the groove in its rim. In this particular machine, we will have a wheel like this that has a rope inside its groove. We could have a load over here and we'll be applying some effort. So this effort, as it is being pulled over here, it is used to raise a load. Now the pulley is also known as the block and tackle system. Now we could have more than one wheel. Some of the wheels are fixed while some are movable. In this machine, the summary is that the velocity ratio of this kind of machine is gotten by counting the number of wheels we will have. So if you have a sketch of a pulley or a block and tackle system such as this, where this is the load and here we have our effort, the velocity ratio is gotten by counting the number of wheels. We have 1, 2, 3, 4. So we have 4 as the velocity ratio. Alright, so next is the inclined plane. Now the inclined plane is a machine that is used for lifting very heavy objects from a low level to a high level, or from a high level down to a low level. So for instance, if we have a vehicle that is as high as this and there is a need to roll a heavy drum on it. Now it may be harder for 2, 3 or 4 people to lift it from down here up into the vehicle. But if we could have a plank, for instance, that will be placed here, such that this is the ground level, and you could have just one or two people roll the heavy drum. It is easily moved up, and the ease at which it is moved up, it depends on the angle over here. So if you get a longer plank, the distance that will be covered in moving the drum up may be longer, but it will be easier. If the theta reduces, then it will be easier to roll the plank. But if you reduce the length of the plank, that means that the theta will increase. When there's an increase in the theta, that means it will be less easier to move the plank. And so from here, we can arrive at a velocity ratio, that the velocity ratio of an inclined plane is equal to distance moved by the effort over the distance moved by load. So where this is the distance that is moved by the load, while this is distance moved by the effort. So we have it that is h over x, and this can also be taken as, now if you consider mathematical equation using sine theta equal to the opposite over hypotenuse. All right, so sine theta equals to opposite, which is x over h. Now to arrive at h over x, so if we decide to juxtapose this, that is to move h up, I will move x down. That means I will have 1 over sine theta. So we have it that 1 over sine theta is also equal to what? The velocity ratio. So we could use this as the formula for velocity ratio, that's h over x equal to 1 over sine theta, or equal to, that is also the velocity ratio. Now we'll talk about the screw. The screw is a form of an inclined plane which is wrapped around a cylinder. Now there are certain features that we should take note of in a screw. Number one thing is that it has a pitch, and the pitch is said to be the distance between consecutive threads. So you have a screw like this. Now if you wrap it around a cylinder, or around something like this, the pitch is the distance from here to here. And then we also have a handle, like when you have to be moving the screw into a particular object. So from all this, we can determine the velocity ratio of a screw by having it as 2 pi a over the pitch, where a is known as the length of handle, and p, that's the pitch, the distance between consecutive threads. We consider the hydraulic press. Now in an hydraulic press, it is made up of a system of pistons, in which here is a load and here is effort, and inside this place we have a fluid that helps to easily move the load from one point to the other. And so the hydraulic press is used in vehicles. When you apply some effort, perhaps you push this, it will move a heavy load upwards because of the fluid, and the fluid helps in reducing friction. Now in an hydraulic press, the velocity ratio is gotten by determining the distance moved. It's gotten by the distance moved by the effort and the distance moved by the load. So we have it as y over x over here. And aside that, we also determine the velocity ratio by considering the area of the piston, that is the circular piston, at the load area and also at the effort area. And then the mechanical advantage can be gotten also by having the load over the effort, or at some time by squaring the radius at the large piston and squaring, let's say this is a small r, the radius at the small piston. This can give us our r2. This can give us our mechanical advantage. So the mechanical advantage is the r squared over r is equal to capital R squared over small r squared, where this r, capital R, is the radius at the large piston, and this other small r squared is the radius at the smaller piston. Now the wheel and axle consists of a wheel with a larger diameter where the effort is applied, and an axle with a smaller diameter where the load is attached. And a typical example is a device for fetching water from a well. In a wheel and axle, the velocity ratio is easily gotten. Now where this is the distance moved by the effort over the distance moved by the load. Now the A over there represents the radius of the wheel, while B represents the radius of the axle. So in one word, the velocity ratio could be taken as 2 pi A over 2 pi B, or it could simply be written as A over B. That's how the velocity ratio is gotten. So next, we talk about the gears, and we said gears follow the wheel and axle principle. The velocity ratio of gears are gotten by the ratio of number of teeth on the driven gear divided by number of teeth on the driving gear. So this is a simple illustration where this is a gear which we are driving, and when I say we are driving, it means that some mechanical energy is driving this, and as this is being driven by the energy, this will set this other gear in motion to achieve a particular aim. So this is the driven gear. Take some questions under machines. The first question says that what does it mean that the mechanical advantage of a machine is 4, and B, that the velocity ratio of a machine is 5. Now when you hear that mechanical advantage equal to 4, it means that the ratio of the load to the effort is equal to 4. That is, the load has 4 and the effort has 1, or other multiples of 4 such as 8 or 1, that's 2, such that when you divide it you get 4. That's A. B, that the velocity ratio is 5. It is similar to that. So in velocity ratio, we are saying that it means that the ratio of distance moved by the effort to the distance moved by the load is 5. So we are saying that distance moved by effort over the distance moved by load is equal to 5. Meaning this is 5 and this is 1. Or we could say that the distance moved by the effort is 5 times the distance moved by the load. Alright, so move on to the second question. A machine with velocity ratio 5 requires 1000 joule of work to raise a load of 500 Newton through a vertical distance of 1.5 meter. Find the efficiency and mechanical advantage of the machine. So in this question, we're given the velocity ratio to be 5 and it has no units. Requires 1000 joules of work, meaning that is our work input, which is 1000 joules to raise a load of 500 Newton and through a vertical distance of 1.5. So distance moved by the load, that's 1.5 meter. We have to determine the efficiency and mechanical advantage of this machine. So all we need to do is make use of our formulas along with the parameters that we have here. Now we have work input, so we have that we can determine our work output from here. Work output is gotten by having 500 multiplied by 1.5, and all these are in the SI units. All right, so this is the work output in joules. So we will have that our efficiency, which is work output over the work input multiplied by 100. Now from here, the work output is 500 times 1.5 and the work input is 1000 multiplied by 100. And so with all this, we will have 50 times 1.5, we have 75% as the efficiency of this machine. And next is to determine the mechanical advantage. We are given the load to be 500 Newton. So next is for us to determine the mechanical advantage. Okay, we are given the velocity ratio to be 5. So we have it that also efficiency equal to mechanical advantage over the velocity ratio times 100. The efficiency we've gotten to be 75 and mechanical advantage is unknown. Velocity ratio is 5 multiplied by 100. So we have 75 equal to 100 mechanical advantage over 5. When we cross multiply, we have 75 multiplied by 5 equal to 100 times mechanical advantage. So mechanical advantage would be 75 times 5 over 100, and that would give 3.75 as the mechanical advantage of this machine. This next question says, in the figure shown, PQ equal to distance from P to Q is 10 centimeter and distance from Q to R is 60 centimeter. Calculate effort, which is E. Now, for us to understand this, we need to understand equilibrium. That is, having a body in equilibrium or moment of a force. So I would refer you to our class under equilibrium. Now here we have a load of 500 grams, which is pulling this ruler down, and we have an effort over here which is balancing it. We have to calculate the effort. So it's about taking moment about a point, which is the fulcrum. So to take moment about this point, we will consider the clockwise movement and the anti-clockwise movement of these forces. All right. Now, so to take moment about these forces, when we consider the movement of this, it moves in a clockwise motion, and when we consider this, it moves in an anti-clockwise direction. So this is clockwise direction, and we have it that sum of clockwise moments is equal to sum of anti-clockwise moments. Before we go on with this calculation, we need to ensure that we change these values into the SI units. So we're given 500 grams. We convert it into kilogram by dividing it by 1000, and then we are left with 0.5 kilogram. That is the mass. And this mass needs to be converted into force or weight. And we have it that weight is equal to mass times acceleration due to gravity. So we have 0.5 multiplied by 10, which is what? 5 Newton. We want to apply this sum of clockwise moments. So we have our clockwise moment to be this. So the mass now is now 5 Newton, which is the weight. So here is the weight multiplied by the distance from here to here. From here to here, we're told is 60. 60 plus 100, that is 70. All right, equal to the anti-clockwise moment, which is this effort, multiplied by the distance from Q, which is here, to P. And the distance from here to here is 10. So multiply by 10. 5 times 7, that's 35, that's 350. Then E times 10. Making E the subject of this formula, we have 350 over 10. So this cancels this. And we are left with effort to be 35 Newton. So that is the effort in this machine. Now we're going to say that this machine is efficient. Well, it's not that efficient because when you consider it, we have a load of 5 Newton and the effort. So the efficiency is going to be, the load is 5 over 35. This is way below 50%, and this machine setup is not efficient. And what order of lever is this? Because this is a lever. Now the order of this machine is a third order lever. Why? Because we have fulcrum, we have our effort at the center, and we have our load. So the emphasis is that the effort is at the center. So this is a third order lever. Next question says, a block and tackle consisting of 5 pulleys is used to raise a load of 400 Newton through a height of 10 meters. If the work done against friction is 1000 joules, calculate A, the work done by the effort, B, the efficiency of the system, C, the effort applied. So in this question, we are given the velocity ratio, because we know that the velocity ratio is the number of pulleys that are given, that is equal to 5, and it is used to raise a load of 400 Newton through that height. So we have a load of 400 Newton, and the distance moved by the load, was given as 10 meters. Now if the work done against friction is 1000 joules, so we have work done against friction, which is 1000 joules. Take note that this friction here, this work done against friction, is what does not help to have an efficiency of 100%. And so this work done against friction, when it is added to the work output, will give us the work input, but we shall get there shortly. Now we have to calculate the work done by the effort first. Alright, so we want to institute over here that work done by the effort. So we want to institute here that work done by effort, that is the same thing as the work input. And we want to establish the fact here that work input is equal to work output plus the work done against friction. Now, our work output can be gotten by multiplying our load by the distance moved by the load, which is 400 times 10, and that gives us 4,000 joules. Hence, the work input, which is this, equal to the work output, that is 4,000 plus work done against friction, which is 1,000 joules. So we have that as 5,000 joules. So that is the first question, that's the work done by the effort. B says we should calculate the efficiency of the system. The efficiency of this system is gotten by the ratio of work output over the work input times 100. The work output in this question that we've gotten here is 4,000, and the work input is 5,000 multiplied by 100 over 1. So with this, we have 4 times 20 as what? 80%. So that is the efficiency of the machine. Next, we are told to calculate the effort applied. Now, the effort applied can easily be gotten. Mechanical advantage equal to load over effort. We know our load, but we do not know mechanical advantage nor the effort. But this could be gotten by having that the efficiency equal to mechanical advantage over the velocity ratio times 100. Efficiency is 80 equal to mechanical advantage over the velocity ratio, which is 5 times 100. So when we cross multiply and get this done, we will have it as 80 multiplied by 5 over 100, and that will give us 4 as the mechanical advantage. Hence, we have it that mechanical advantage equal to load over effort, and so our effort is equal to the load over mechanical advantage. The load in this question is 400, while the mechanical advantage is 4. So the value of effort is equal to 1,000 Newton. So 1,000 Newton is the effort, 80% is the efficiency, and 5,000 is the work input. An inclined plane of angle 30 degrees is used as a simple machine. What is its velocity ratio? Now this question says that the velocity ratio is unknown, but we're given the theta. For instance, this is the inclined plane, and we have a theta of 30 degrees. So we have velocity ratio equal to 1 over sine theta, that is 30 degrees. That is 1 over 0.5. The velocity ratio is equal to 2. Next question says, in a hydraulic press, the areas of the small and the large pistons are 4 cm squared and 600 cm squared respectively. Find the velocity ratio of the machine. Assuming there is no friction, find the mechanical advantage. Here, we are given the area of small piston to be 4 cm cubed, and area of the large piston as 600 cm, and we are aware that the velocity ratio can be derived by the ratio of the large piston to the small piston. So we have it as the large piston is 600 and the small piston is 4. When we divide it, we have 150 as the velocity ratio. And the second part of this question says that, assuming there is no friction, find the velocity ratio. Now, if there is no friction, mechanical advantage will be equal to the velocity ratio, meaning that the velocity ratio also will be 150. Next question says, an electric pump with efficiency 70% raises water to a height of 15 meters. If water is delivered at the rate of 350 dm cubed per minute, what is the power rating of the pump? Taking into consideration that mass of 1 dm cubed of water equal to 1 kilogram. B, what is the energy lost by the pump? Taking gravity to be equal to 10 meters per second squared. Here we have the efficiency of a pump as 70%, and it raises water to a height of 15 meters, and then it delivers the water at the rate of 350 dm cubed per minute. So we have 350 dm cubed per minute. Let's take note that this is per minute. We are to consider the power rating of the pump. First, we know that efficiency equal to work output over work input times 100. In this question, we were given power, and so work output is the work done or the energy that is expended over time. Alright, so in this question, the work output is the work done or energy expended per time. And if you look at our question, we were given 350 dm cubed per minute as the rate at which water was delivered. So we have it that work output is the work done over time. The work output is the rate at which the water was delivered, and we have it as 350 dm cubed per minute. Now we need to convert this into the right units. We have that 1 dm cubed of water is equal to what? 1 kilogram, meaning that 350 dm cubed is equal to what? 350 kilogram as well. Then we're given per minute. The minute needs to be changed into the SI unit, which is seconds, and per minute means divided by 1. So to change it into seconds, that will be divided by what? 60. Do not forget that when we are considering power, the fact that power was used to carry out the work, power is equal to work done over time. And our work done, we call it the work output here. So the work done is equal to force times distance over the time in which the work was done. So we will change this 350 kilogram into force, and that is gotten by having 350 multiplied by 10. That is mass times gravity times the distance through which the work was done, which is 15 meters. So we have our 15 over here over the time, which is 60. And so when we calculate this, we will have 875 watts. So we have this as the work output. We are to calculate the power rating of the pump, and the power rating of the pump is the work input, that is the work that the pump can do per time. That is the work input. The work output we have gotten over here, it is the work that was done per time. So we have it that the efficiency now is equal to the power output over the power input times 100. The power output here, so we can make this work output to be power output. So the power output here is 875, and the power input is unknown, and our efficiency is what? 70 times 100. When we multiply this, we will end up having that x equal to 875 times 100 over 70, and that would give 1250 watts. So 1250 watts is the power rating of this pump, or the power input. Then the other part says that what is the energy lost by the pump. To get the energy lost by the pump, first we need to get the power loss, and the power loss is going to be the power input minus the power output. The power input is 1250, and the work output is 875, and that would give 375 watts. That is the power loss. And we know that power equal to work done over what? Over time. So the power we are having here is 375 over the work done, which we are looking for, over time, which is given in 60 seconds. So work done will be 375 multiplied by 60, and that will give us 22,500 joules, which is equivalent to 22.5 kilojoules. That is the energy lost by the pump. Alright, so in this next question, we are told that a machine is used to lift a load of 20 Newton through a height of 10 meters. If the efficiency of the machine is 40%, how much work is done? Here, the load is 20 Newton, and the height that the load lifts it through is 10 meters. The efficiency of the machine is 40%. How much work is done? Alright, so we have it as our efficiency is work output over work input times 100, and we are looking for how much work is done. So that is the work input that we have to look for. The work output can easily be gotten by saying the load multiplied by the height moved by the load, which is 20 times 10, that is 200 joules. Efficiency is 40%. The work output is 200 over the work input times 100, Making work input the subject of this question, we have 200 times 100 over 40, and that will give 500 joules. So here is the work input or the work that is done. This next question says the efficiency of the pulley system shown is 80%. Find the efforts required to lift a load of 1200 Newton. This is an example of a block and tackle system, and the velocity ratio is gotten by counting the number of pulleys that we have there, which is 4. We are told the efficiency is 80%. We are to find the efforts. So we have that efficiency equal to mechanical advantage over the velocity ratio times 100. Efficiency is 80, mechanical advantage is unknown, and the velocity ratio is 4 multiplied by 100. So making MA the subject, we would have 80 times 4 over 100, and that would leave us with 3.2 as the mechanical advantage. But that is not where we are stopping. We are to determine the efforts. Here we have that the load is 1200 Newton. Mechanical advantage equals load over effort. So 3.2 equal to 1200 divided by the effort. Making effort the subject of this formula, we have 1200 divided by 3.2, and that leaves us with 375 Newton as the effort. A wheel and axle is used to raise a load whose weight is 800 Newton when an effort of 250 Newton is applied. If the radii of the wheel and axle are 800 mm and 200 mm respectively, find the efficiency of the machine. We are given the radii of the wheel and the axle. So the velocity ratio equal to radius of wheel over radius of axle. That of wheel is 800 and that of the axle is 200, and so we'll have 4 as the velocity ratio. Next, we have to look for the mechanical advantage, which is load over effort. We're given a load of 800 Newton and an effort of 250 Newton, and that gives us 3.2 as the mechanical advantage. Now we can easily calculate the efficiency, which is mechanical advantage over the velocity ratio times 100. The mechanical advantage is 3.2, and that will yield 80% as the answer. What effort will a machine of efficiency 90% apply to lift a load of 180 Newton if its effort arm is twice as long as its load arm? So we are looking for the effort, which is unknown, and the efficiency is 90%. Move a load of 180 Newton if its effort arm is twice as long as its load. So with this, if you are taking it that it is twice as long, so we can say that is the velocity ratio is the effort distance to the load distance is 2:1. That is what it means. So meaning that the velocity ratio is 2/1. So from here, what we will do is to get our effort first is to calculate the mechanical advantage. And we know that the efficiency equal to mechanical advantage over velocity ratio times 100. Efficiency is 90% and mechanical advantage unknown. Velocity ratio is 2 multiplied by 100. Making mechanical advantage the subject, will have 90 times 2/100, and we will be left with 1.8 as the mechanical advantage. Then next we have mechanical advantage equal to load over effort. Mechanical advantage is 1.8, load is 180 over effort. So effort equal to 180 over 1.8, and that will leave us with 100 Newton. Here's the question which says that in a hydraulic press, the pump piston exerts a pressure of 100 Pascal on the liquid. What force is exerted in the second piston of cross-sectional area 3 meters squared? Now in this question, we shall be taking an assumption that there is no friction in this hydraulic press. So with that, it means that the work output will be equal to the work input. So here, in the first piston, it has 100 Pascal. And what is going to be the equivalent in the second piston? Meaning that it will be 100 Pascal as well. So with this, now Pascal is the unit of pressure. Pressure is equal to force over area. We have the area as 3, so pressure is 100, force is unknown, and the area we're given in this question is 3. Hence, the force will be 100 multiplied by 3, and that is 300 Newton as the force. This next question says that a wheel and axle is used to raise a load of 500 Newton by the application of an effort of 250 Newton. If the radii of the wheel and axle are 0.4 cm and 0.1 cm respectively, the efficiency of the machine is what? So this question is quite straightforward in that we can calculate our mechanical advantage by saying load over effort. The load given here is 500 Newton and the effort given here is 250 Newton. The velocity ratio in this wheel and axle will be the ratio of radius of wheel over the radius of the axle. The radius of wheel given in this question is 0.4 and the radius of the axle is 0.1, and this will give us what? 4. And over here too, 500 divided by 250, that gives us 2. So we have to calculate the efficiency of this machine, and we know that efficiency equal to mechanical advantage over velocity ratio times 100. Mechanical advantage here is 2, velocity ratio is 4 multiplied by 100. So we are left with 100 over 2, that is 50. So the efficiency of this machine is equal to 50%. So to solve questions under machines, all you need to do is know your parameters and the formulas, apply them, and you'll get your answers.